So we're going to start with a recap of the remainder of Chapter 2, and we're going to review our adiabatic lapse rates and our precipitable water. So where we ended last time, we talked about the adiabatic lapse rate. So the first adiabatic lapse rate is the dry rate, which is approximately cooling at 10 Kelvin per kilometer cooling. Okay, and so this is generally a linear trend as the parcel rises in the atmosphere. There's also a wet or moist adiabatic lapse rate, which cools 5 to 8 Kelvin per kilometer. And this is cooling, and this is when we have a condition when temperature is equal to our dew point temperature. When we have our dry rate is when our temperature is greater than our dew point. And actually, technically, this is less than or equal to our dew point. So in this case, we have dew. In this case, we do not. There are two very distinct rates, two very important cooling mechanisms to understand. So if we have the atmosphere, here we have a cloud, we have the ground. So from this elevation to this elevation, we experience our dry rate. Again, our parcel is cooling as it rises. And in here, we have our moist adiabatic lapse rate. And remember, it is still cooling, but not as quickly, or not as much, I should say, because of what mechanism? Why is it not cooling as quickly in the cloud? It has to do with the transition from vapor here into liquid. Okay, vapor to liquid, which is causing the release of our latent heat of vaporization. Vapor to liquid. Okay? These are very, very important values that you're going to be using a lot, especially when we start getting into the precipitation chapter. The second thing we are going to review is precipitable water. And what we can recall from this is the maximum possible rain to get in a column of air. This doesn't mean that this is the amount of rain we're going to get. So WP does not necessarily equal precip. It's just the possible amount of rain you could get. It's the perhaps achievable, but there's always going to be vapor in the atmosphere. Again, this is just what could potentially happen. So the next thing I'm going to do is introduce you to a very important data set where you're going to be using a NASA product. And actually, you're using this same product for your homework, so I figured I would explain the data set before you had to go tackle that problem. So the data set you're going to be using is the Atmospheric Infrared Sounder AIRS data set, which is a NASA JPL product. It is approximately a 1 degree by 1 degree grid cell, which makes it actually very easy to use. It's basically a matrix, right, where you have the globe broken up into perfect squares. Now, it's 1 degree by 1 degree, and it goes from your negative 180 west to positive 180 east. Okay, so 360 degrees total in the longitude. The longitude is along the x-axis. Now, the latitude is going from positive 90 degrees to negative 90 degrees, north-south, and so this is your y-coordinate, which is latitude. It does say that here, but I just wanted to draw a picture so you could follow along. Now, since everything is 1 degree by 1 degree, right, that means that this is in the x-axis, you're going to have 360 cells, and in the y-axis, you're going to have 180 cells, just as an FYI. Now, in this particular product, you're provided temperature and water vapor profiles for 24 temperature pressure levels or 12 H2O pressure levels. So this is actually the one we're going to be using. So what this is saying is this data set is not only gridded in the X and Y direction, it also has depth in the Z direction. So you have water vapor estimates at 12 levels of the atmosphere. That's what this is saying. Now, the water vapor profile that we're going to be using is specific humidity. Specific humidity is always going to be your mass of water given the mass of air. Now, the units that these particular profile is given is in grams over kilogram. So this could potentially lead to a problem, okay, when you're doing your calculations, because you have to make sure that your units do cancel. So we are going to have to convert this to kilogram per kilogram, just as an FYI. Now, if there is a value of negative 9999 or a count of 0, it indicates that there is an invalid or missing data set. So you're going to also have to make sure that you're catching all missing data sets when you're doing your evaluation. So these are the pressure levels of observation. So this column here is your column of interest, really, where it says values of H2O vapor at the levels. So these are the pressure levels in the atmosphere where we receive the observations. So here it says that the observation is in hecapascals, where heca just means 10 to the 2 Pascal. That's what the hecapascal means. And now let's look at this for a second. So what do we know about the pressure of the air as we rise in the atmosphere? So pressure decreases as we rise in the atmosphere. So that means that at 1,000, so at this level, we are at the surface. And so this means in this direction, we are rising in the atmosphere. So here is when we're at the top of our atmosphere. Here. Okay? So generally speaking, you're going to see most of your precipitable water in these lower levels, because remember when I explained that most of the water is trapped in the troposphere and in the mesosphere and really doesn't go too much further beyond that. So you're probably going to get a bunch of zeros here, and this is where you're going to get the bulk majority of your precipitable water. Okay, so unfortunately for this part, you are going to have to use Matlab to load the file. here is the file name, and this is exactly how you load in Matlab. So you can just copy and paste this script in Matlab in the same, so it has to be in the directory where your file is saved. It has to be. So load in your file in Matlab, and then you can copy and paste this script into the editor. I'm gonna do like a kind of sample of how to do this, and you're gonna load in Matlab. When you do that, your vapor LV, this variable here, is going to have these dimensions. So the first dimension corresponds to the pressure layer. So this is going to be your pressure layer, and this is actually in your rows. This corresponds to our latitude, and this is our columns. This corresponds to our longitude, and this is actually in the z direction. So you can have a variable that has 1, 2, 3 dimensions. Okay, so let's say you wanted to grab all latitude and longitude at the surface. Well, according to the previous slide, the surface is going to be the first layer number here. So it would be vapor LV, layer number 1, all latitude, all longitude. And what this will do is this will give you a 2D surface where the latitude is going to be essentially, if you wanted to do an image scan of this, the latitude would be on the y-axis and the longitude would be on the x-axis. So in order to calculate the precipitable water using the particular data set, we're going to follow this equation here, which is saying that the summation, right? So this is 1 over G, and we're going to look at the summation of Q at all these Z's, okay, multiplied by PS minus P, okay? So that's what this integral represents here, okay? So this needs to occur across the Z's, but also at every X and Y location, right? Which in Matlab, what this translates to is you're going to have a for loop looping your I indices. So these are going to be your rows. And you're going to have a for loop looping your J indices, which are going to be your columns, to get the sum of your water vapor. So then you're going to sum vapor at IJ for all Z's, okay? So when you're grabbing all your Z's, you're just grabbing vapor LV. So you're grabbing vapor LV, all 12, and you're pivoting your IJ, okay? And then you're going to do the sum and the sum and the sum and the sum and the sum. So this should be your product, which is going to be 2D, because you're summing across, you're summing across all of the elevations. That's kind of a hint on how to get your homework started. And if you're not proficient in Matlab, again, I will revisit this problem, and I will help you in office hours to get you through this problem. It is important that you use the NASA dataset because I am affiliated with the NASA JPL cohort, and we want students to learn how to use the products. So this is basically the equation you're going to end up with, where the precipitable water at every x and y location is 1 over gravity multiplied by that summation multiplied by the change in pressure. So this is going to correspond to your pressure at the surface, which we know is at the first position for various of your input. So vapor LV1, and this is going to be at the end, which is going to be at the top, right? These values should be the 1000 hecapascal and the 100 hecapascal. You're going to have to watch all of your units just like you would in any other class. Your precipitable water units, just as an FYI, should be kilograms meter per second squared. So just something to achieve. Make sure that this is in kilogram. We all know our gravity units, and make sure this is converted to consider the Hecca. Here is what you should achieve. Okay, so I'm kind of showing you the answer. Is at every single x and y coordinate for your latitude and your longitude, you're taking the sum of your precipitable water, you're multiplying it by that change in pressure. So again, this change in pressure, and dividing by gravity for every single cell in your domain. That is what you are doing. Okay? I hope that makes sense, and here are some sample calculations if you wanted to try for the homework while I'm gone. So now we're going to start Chapter 3 and radiation processes. I'm mainly just going to go over definitions to kind of set the stage before we get into heavy equations next time. Trying to take it easy on you guys while I'm gone. So first we're going to start with some definitions, kind of get into radiation processes, and really it's a review of physics. So here we're going to start with, radiation, okay, provided by the sun is external forcing on Earth system that drives 1, the hydrologic cycle, and 2, atmospheric and oceanic motions. Okay, so the sun comes out every single day. We really do take it for granted. All of the energy that we receive from the sun is used for many, many processes in nature, as well as in movements of water vapor for our hydrologic cycle. So radiation or energy is strongly related to water fluxes, okay? So we need to understand mechanisms responsible for variability in radiative fluxes by developing models for estimation. Okay, so radiation is the main driver for a lot of our processes in the atmosphere. So I'm just kind of setting it up as like, this is really important. Again, we're going to review a lot of your physics. So what is electromagnetic radiation? Electromagnetic radiation. So electromagnetic radiation are waves traveling at the speed of light and are characterized by wavelength, which we denote as a lambda, or frequency, which I've seen a frequency expressed as a little c, but in this particular book, he expresses it as a VU. So lambda multiplied by your frequency, so wavelength multiplied by frequency is equal to c, which again is the speed of light. So good thing we changed that. The speed of light is a constant and is approximately 3 times 10 to the 8 meters per second. So it moves pretty fast. Okay. Now wavelength, so lambda has units in meter generally, and frequency has units in hertz, which are 1/second. So we basically see a wave so many times per second, and that wave is a certain amount of meters long. So we have a wide spectrum of wavelengths varying from short to long. So this is a graph representing the short wavelength here on the left-hand side of the graph, and then as it moves into the longer wavelength. So I want to just review some important categories here. So gamma rays, X-rays, ultraviolets, these are very short wave radiation. Do you see here we have on the magnitude of 1 times 10 to the negative 4 micrometer to 1 micrometer. So they're very short in wavelength, and these are very dangerous. Here we have visible light. So this is the wavelength for visible light. As you go from purple to red, the wavelength gets longer. So this is 0.4 micrometers to 0.7 micrometers. We have infrared. So once we head actually past visible light and into infrared, this is where we have our long wave radiation. So everything from this point on is our long wave. And this point this way is our short wave. Okay? Now just for some notes, our ranges for long wave and short wave are about, so short wave again is from like 0.0001 micrometers to about 1 micrometer, and long wave is about 1 to 10 micrometers to 1,000 meters. So the long waves can be incredibly long. Now, kind of the microwaves we're very used to, right? Super long waves, not really not dangerous at all. Super long radio waves, not dangerous at all. So that those frequencies that when you turn the dial on the radio station, they correspond to the certain long wavelengths. A really important definition that we learn from physics is something called a blackbody. So from physics, we know every body emits radiative energy according to this equation. So the radiative energy that your body emits at a certain wavelength is equal to your emissivity multiplied by this blackbody emission. So this is your radiation emitted per unit area per unit wavelength. This is your spectral emission or emissivity, which is a function of lambda. And this B here is called a black body emission at lambda. So a few things to explain here. Okay, so the units for R at lambda as well as B at lambda is the radiation, so radiative energy emitted per unit area. So energy is measured in watts per unit area per meter squared per unit lambda, which is going to be per micrometer. So those are going to be your units for your radiation fluxes and your black body. So that must mean your emissivity units are going to be nothing. Okay, it's going to be unitless. Okay, now I want to explain what these two entities are in greater detail. What this equation represents is that this emissivity is going to range from 0 to 1. So it's going to be some fraction. Okay? That means that whatever radiation your body emits is going to be a fraction of whatever this B lambda is. So this is a fraction of B lambda. So what is B lambda? B lambda is called the black body, which is a perfect emitter. Okay? We are not perfect. No, land is not perfect. Ocean is not perfect. So every single thing on Earth has some emissivity, some fraction of energy that we're able to emit. The only thing in the universe that is considered A black body is the sun. So this is radiation from the sun, and only the sun, at a given wavelength. Okay? That is the black body. Black body is going to be the sun. Okay? The only thing that it will ever be is going to be the sun. Okay? There are some derivations in your book that uses the Stefan Boltzmann and Planck constant in order to integrate and calculate our black body emissions. I'm just going to kind of show this graph to kind of explain what the black body spectrum looks like. So here, do you see these two color lines? So this line here corresponds to the emission from the sun, this yellow line here. So let's take a look at this. So remember, this spectrum is the short wave, and this spectrum is the long wave. What do you notice about the spectrum emission from the sun? Well, the sun emits at all wavelengths. According to this graph, where the temperature of the sun is approximately 5,777 Kelvin, okay? According to this graph, the radiant emittance it spans the entire spectrum. So emits at all wavelengths, both short and long wave. Okay? Now, before I move on, what is the bulk majority of the sun emitting? Is it mostly emitting short wave, or is it mostly emitting long wave? So the sun peaks here at the short wave spectrum. So it emits a lot of visible light. So we generally say, although the sun emits at all wavelengths, the sun mostly emits within our shortwave spectrum. Okay? Now let's observe this line here. So this is the sun, and this line, is the earth. So the earth temperature is approximately 300 kelvins, okay? And it primarily emits what type of wavelengths? It primarily emits in the long spectrum. So the Earth only emits long waves, okay? Only. So the Earth technically does both short and long, but mostly does short. The sun does both short and long, but mostly emits in the short. The Earth only emits in the long wave, okay? So these are very important definitions that we need to set up. So far, we've been talking about everything as a function of wavelength. Well, we actually don't want to express everything as a function of wavelength. We want to integrate across the wavelengths in order to get our total radiative flux. So for the sun, we have our ultraviolet and our visible spectrum, which ranges from 0.1 micrometers to 4 micrometers. And we have our Earth spectrum, which is all infrared, or long wave radiation, which ranges from approximately 4 micrometers to 100 micrometers. So this is the Earth range, and this is the solar or the sun range. So what we would like to do is kind of identify these two as very, very important and very different spectrums. So we're breaking this up and saying we want to look at the radiation from the sun and the radiation from the Earth. So these are called two very different things. So we basically call this our short wave radiation, and this is going to be our total radiative flux. So for the short wave, it's going to be the integration from 0.1 to 4 micrometers of that radiative energy multiplied by that wavelength. So this is going to be our total radiative flux, and this gives us watts per meter squared. So energy per area. That is going to be our total radiative flux for the shortwave spectrum. Similarly, we have something for the long wave spectrum where we integrate from 4 to 100 micrometers, R sub lambda, d lambda, and this also will be in watts per meter squared. So these are very, very, very important fluxes. And all we had to do was integrate over our spectrum. So we essentially said, give me the total radiation due to the shortwave spectrum, and integrate and give me the total long wave across this spectrum, okay? So this is a very good stopping point. I need you to review these concepts before we start the next lecture, because the next lecture is when we're actually going to come up with ways to estimate and models to predict the shortwave calculation and the long wave calculation as a function of temperature and time of year and things like that. So it's a lot of changes that go on with these calculations.